This is the second part of the discussion on the Bohr model. Another relevant equation that you have to take note for this lesson is the energy of the quantum states. So Niels Bohr was able to come up with a formula that allows him to solve for the energy associated with an electron at a specific energy level n. And it is actually this equation. It looks fancy, but all of these can actually be simplified with a constant. After all of these are constants, so therefore we could express this particular equation as the energy associated at a certain energy level n is equal to negative 13.6 divided by n squared, and this is expressed in electron volt. The negative sign here tells us that the electron is bound with the nucleus, since the nucleus is positive, so electron is bound with the nucleus. So using this equation, we would be able to solve for the energy of the electron when it is on its ground state, or when n is equal to 1. So at ground state, n is equal to 1, and the energy associated at ground state, or the energy of the electron when it is on ground state, is just equal to negative 13.6 divided by n squared, and our n is equal to 1, and this is in electron volts, so therefore the ground state energy is equal to negative 13.6 electron volt. Consequently, the energy of the electron on the second energy level, so we would substitute n to 2, so we will have negative 13.6 divided by 2 square, and this would give us negative 3.4 electron volt. So once again, I would like to stress out that when we talk about ground state, that means n is equal to 1. Now let's talk about the ionization energy. The ionization energy is just the energy needed to completely remove the electron from the atom. So if we're talking about the hydrogen atom having 1 proton and 1 electron orbiting around it on the first energy level, this electron being on the first energy level possesses an energy equal to negative 13.6. Again, the negative sign tells us that the electron is attracted with the nucleus. Now, in order for us to liberate this electron over here, it must gain an energy equal to the energy that it possesses in order for us to remove this electron completely from the atom. So therefore, the ionization energy of the hydrogen is 13.6 electron volt, meaning these electron here must receive or must absorb an energy equal to 13.6 in order to completely free this electron from the hydrogen atom. Alright, so with the equation E sub n is equal to negative 13.6 divided by n squared, and this is in electron volt, this tells us that the uppermost level would correspond to E is equal to 0, and that is because n here would approach infinity. So therefore, when you're very, very far from the nucleus of the atom, the farther you are from the nucleus of the atom, the less energy you're going to, or the electron is going to possess. So in fact, in the uppermost energy level, that is n approaching infinity, the energy at that point is equal to 0. Now let's look into Rydberg's equation once again. So whenever a transition occurs between a state Ni to another state Nf, or when electrons move back from a higher energy level Ni to a lower energy level Nf, a photon is emitted. and the energy of this photon is equal to the amount of energy that the electron absorbed in order for it to jump from a lower energy level to a higher energy level. So once again, in order for it to go back to a lower energy level, it has to emit the energy that it has absorbed in a form of a photon. And the wavelengths of these specific photons can be solved using Rydberg's equation, which is equal to 1 over lambda is equal to RH, the Rydberg's constant, multiplied by 1 over n final squared minus 1 over n initial squared. And this is actually very similar to the previous Rydberg equation, which is this, multiplied by 1 over m squared minus 1 over n squared. It's just that our m here is the n final, or the final energy level, and then the n here is the initial energy level. And for the Paschen series, n final is equal to 3. So we have here, this is actually the final energy level if we talk about Paschen series. For the Balmer series, the final energy level is the second energy level. And for the Lyman series, the final energy level is the first energy level. Now, it is also worth noting that for Paschen series, infrared radiations or the photons are most likely in the infrared radiation, whereas in the Balmer series it's in the visible spectrum and some visible spectrum and UV. Whereas for the Lyman series, it's purely UV. So the photons emitted as electrons move from a higher energy level towards energy level 1, that is for the Lyman series, they are going to emit a photon in the UV spectrum. One of the objectives for this lesson is for you to be able to state Bohr's correspondence principle. Here is the statement. Bohr's corresponding principle states that quantum mechanics is in agreement with classical physics when the energy difference between quantized levels are very small. This is particularly useful in predicting the wavelength of the photon that will be emitted by an electron as it moves from a higher energy level to a lower energy level. Now, this equation would be true if your initial energy level is close to the final energy level. So we'd say, for example, n final is equal to 2 and n initial is equal to 4. So they are relatively close to each other. However, when your initial energy level is very, very big compared to your final energy level, the Rydberg's equation may not be able to accurately predict the wavelength of the photon that the electron is going to emit, and therefore quantum physics is no longer in agreement with classical physics. The analysis used in the Bohr theory is also successful when applied to hydrogen-like atoms. Now, an atom is said to be hydrogen-like when it only has one electron. So examples of that would be a singly ionized helium, so He positive 1, or a doubly ionized lithium, so that would be Li positive 2, or a triply ionized beryllium, Be positive 3. So all of these would contain one electron and therefore may be treated as hydrogen-like. Now, to solve for the energy associated with the energy levels in hydrogen-like atoms, we have this equation, and it is very similar to the energy in each quantized state in a hydrogen atom, which can be solved using the equation En is equal to negative 13.6 divided by n squared, and this one here is electron volts. So the only difference for hydrogen-like atoms is the inclusion of the atomic number Z. Also, the wavelength of the photon that will be emitted by the electrons of hydrogen-like atoms can be solved using this equation, and this is very similar to the wavelength of the photon that is emitted by a hydrogen atom, which is actually this equation. Let me just write it down. Minus 1 over Ni squared. And the only difference, again, is just the presence of the atomic number. And that concludes our lesson on the Bohr's model of the atom. Now, I need you to log into WebAssign and do the task, the Bohr's model, part 2.